Welcome back to the deep dive. Today, we're really getting under the hood, pulling apart the technical foundations of a pretty ambitious new blockchain project called Gravity Chain.
That's right.
We've got the Gravity Litepaper here, plus, the related docs they've put out.
Yep, the whole structure.
And our mission really is to cut through maybe some of the hype, some of the jargon, and pull out the core ideas, the actual innovations they're describing.
Mm-hmm. How are they actually proposing to hit these big performance numbers they talk about?
Yeah, how do they plan to deliver high throughput, low finality, solid security? That's what we want to figure out from this material.
Exactly. Well, sticking just to what's in the documents here, trying to understand the engine they've described, what are the key technical bets they're making?
And some of those bets or claims are, pretty eye-popping.
Definitely.
I mean, the light paper mentions things like 1 gigas per second throughput.
It's just massive.
And sub-second finality. I mean, compared to a lot of what's out there, that sounds fast, like incredibly fast.
It really does. Almost warp speed, like he said.
Okay, so let's unpack all of this for you. Think of this session as your guide, your way to navigate the architecture, the key technical pieces they're describing in these documents.
Let's do it.
Ready to jump in?
Absolutely. Let's dig in.
All right. So the first thing the sources highlight is kind of the why. The origin story, you could say. It seems the push for Gravity Chain really started with Galxe.
Right. The Web3 application platform. Big one.
Huge. And the docs mentioned they have just a ton of activity, especially around things like loyalty points, token reward campaigns, that kind of stuff.
Yeah, the numbers are quite something. The paper notes, like over 51 transactions per second just for loyalty points on average.
Mm-hmm.
And another 32 for token rewards.
That's already pretty significant volumes.
It is. And what's interesting is how Galxe's own success basically revealed a bottleneck as they started thinking about moving their entire back-end on-chain.
Which is a big step.
A huge step. They apparently ran smack into the limits of existing chains. They needed something that wasn't just high volume, but also had that near-instant finality. That smooth user experience was critical.
Okay, so that leads to this fundamental choice point the document lays out. Do we build on an existing layer 2? Or do we go all in and build a brand new layer 1?
That's the core dilemma they presented.
Yeah.
And the deciding factor, the thing that pushed them towards a new L1, according to this material, was transaction finality.
Finality, okay.
Yeah. As the sources explain it, L1s, particularly ones using the kind of BFT consensus they ended up choosing, tend to offer much faster time to finality than L2 rollups.
Even with ZK proofs and things.
Even with those advancements, rollups often still have these challenge periods, right? Which can mean waiting hours, sometimes even days, for like true finality. Whereas the sub-second finality, which they say a BFT-based L1 consensus can achieve, was presented as absolutely essential for Galxe's users and their whole setup.
So wait, even if an L2 could maybe handle higher peak throughput theoretically, by offloading work, the finality speed was the non-negotiable part.
That seems to be the argument presented, yes.
But hang on, building a new L1. Historically, that's always come with this massive headache. Bootstrapping security. How do you get enough validators, enough stake, to make it secure from the start? How do the docs say they tackle that?
That's a really critical question, and it's where this idea of restaking comes in. It's central to their whole approach, based on this paper.
Okay.
The material explicitly says that with new protocols emerging, like EigenLayer and Babylon, that big challenge of bootstrapping L1 security is, well, significantly reduced.
So they're leveraging those.
Exactly. Gravity Chain, as it's described here, integrates these. It essentially lets them tap into the huge amount of staked value that's already securing networks like Ethereum.
Which is massive.
Tens of billions, yeah. And Bitcoin, too, potentially hundreds of billions via Babylon, is the projection mentioned. So by using Ethereum's validators and Bitcoin assets through these protocols, they aim to inherit economic trust and security right out of the gate.
So it sidesteps the cold start problem for security.
Precisely.
Yeah.
And specifically addresses concerns like long-range attacks that new POS chains can face.
Okay, that makes sense. So the motivation is clear. High volume needs from apps like Galxe, the crucial requirement for super fast finality driving the L1 choice, and then restaking solving the security bootstrapping issue.
That's the picture painted in the documents.
And the sources also mention that the tools they're building, like the Gravity SDK and their execution layer, Grevm, they're designed to be more general purpose, not just for Gravity Chain itself.
Yeah, they position it as a flexible framework, kind of like how the Cosmos SDK works, for building other chains too. The vision presented is definitely broader than just this one initial chain.
Interesting. Okay, but let's zoom back in on those headline numbers for a second. That 1 gigas per second claim. How do the sources actually justify needing that kind of capacity? It seems enormous.
Well, they start with Galxe's current usage as a sort of baseline.
Right.
Based on the volume we mentioned and some estimated gas cost per transaction, they figure Galxe's loyalty points alone need something like 4 million gas per second right now.
Okay, 4 million.
And they say they validated this number using data from an experimental L2 they ran called Gravity Alpha Mainnet.
And then they just extrapolate from there, projecting growth.
Pretty much. They look ahead, assuming Galxe eventually moves its entire back end over, and estimate peak times could demand maybe 50 million gas per second.
Wow, okay, that's a big jump.
It is, but they don't stop there. They then factor in a whole potential ecosystem. DEXs, NFT stuff, cross-chain settlement protocols, the works.
Right, other apps building on Gravity.
Exactly. And using some kind of Pareto distribution model for how gas might be used across these apps, they project the total ecosystem demand could hit maybe 500 million gas per second.
Half a gigas.
Yeah. So to give themselves plenty of headroom, make sure performance isn't a bottleneck, even for really intensive future apps, they conclude that targeting 1 gigas per second is actually necessary.
That's quite the scaling plan. So what's the absolute core piece of tech described in the paper that supposedly makes that kind of throughput possible?
Well, one of the absolute keys they highlight is parallel EVM execution.
Okay.
The source introduces something called Grevm. That's their parallel EVM runtime. They benchmark it in the paper and claim it's the fastest open source parallel EVM available. Well, to date, as they wrote it.
Fastest by how much, though? Do they give specific numbers?
They do, yeah. They provide benchmark figures.
Yeah.
So in a sort of perfect world scenario, no transaction conflicts at all.
Highly idealized.
Very idealized, yes. Grevm is shown hitting 26.5 gigas per second, which they say is about 4.1 times faster than just running things one after another sequentially.
Okay, still impressive.
But more realistically, when they simulate I/O latency, waiting for data from storage.
Which always happens.
Always happens. It's still apparently way faster.
Yeah.
The benchmark shows it achieving 6.8 gigas per second, which is over 50 times faster than sequential execution in that specific test.
Ooh, okay. Over 50x faster with I/O lag simulated. That's genuinely impressive if accurate.
It's a dramatic difference, yeah. And it comes from its ability to run transactions in parallel and handle those I/O operations asynchronously without blocking everything else.
So how does Grevm actually do that? What's the trick to running them in parallel?
According to the document, it builds on a library called Revn and takes inspiration from another approach called Block STM.
Okay.
The basic idea is using hints about data dependencies that they get from simulating transactions before they're fully executed.
Simulating them like when they first appear.
Yeah, for example, as they arrive in the mempool, they simulate them to guess what state they might read from or write to. This lets them build a sort of map, a graph, showing potential dependencies or conflicts between transactions. That graph then guides how they schedule the transactions for parallel execution, trying to minimize the chances they'll have to rerun transactions if a conflict actually pops up.
So it's like, guess what they'll do? Map out the potential conflicts, then run as many as possible at once based on that map.
That's pretty much the three-phase process they outline. Hint generation and state preloading, the simulation part, then dependency analysis, building that graph, often called a DAG, and finally concurrent execution with conflict resolution, which uses the graph and a modified block STM approach to run things and handle any issues.
Got it. Okay, let's switch gears back to finality for a moment. They wanted sub-second finality. How do the docs say that is achieved?
Right. The choice of the consensus algorithm itself is absolutely fundamental here. They use something called Aptos BFT.
Based on Aptos, okay?
Yeah. The source material describes it as, a state-of-the-art proof-of-stake consensus protocol from the PBFT family.
PBFT, right, known for faster finality.
Exactly. And they specifically highlight that Aptos BFT includes an optimization called order votes, documented in an Aptos improvement proposal, AIP 89. This apparently reduces the number of network communication hops needed for consensus down to just 3.
3 hops.
3 hops, which the document states is the theoretical minimum for a BFT-style protocol. So that directly contributes to hitting that super fast finality target.
Okay, consensus is fast. But where does this pipeline idea fit in? How does that connect to finality and throughput?
Ah, the pipeline. So the
Yep.
Gravity SDK introduces this 5-stage pipeline structure. The main goal, as the docs describe it, is to try and close that throughput gap you often see between L1s and L2s,
Right.
but without giving up that low finality advantage of the L1.
How does pipelining help with that?
It works by interleaving tasks for different blocks at the same time. So, for instance, while the consensus process is figuring out the order for block number 101, the execution layer could already be running the transactions for block number 100.
Ah, I see. It's overlapping the work down an assembly line, basically. Different stages working on different blocks concurrently.
Precisely. It's designed to keep all hardware resources busy and cut down the overall time it takes to get a block fully processed and finalized by having multiple stages active simultaneously across the block sequence.
Okay, that makes sense. And tying back to security one more time, the sources really hammer home restaking again. Why is it framed as so utterly central to their L1 design?
They present it as a very deliberate architectural choice to balance 4 key things: security, throughput, time to finality, and also interoperability.
Okay.
The restaking module is the specific component that plugs into protocols like Eigenlayer on Ethereum and Babylon on Bitcoin. That's what provides the economic trust layer needed for their proof-of-stake consensus to be secure from day one.
So they're essentially borrowing or maybe renting the security guarantees from these much larger established networks.
That's exactly the idea presented. By becoming what's called an actively validated service, or AVS, on Ethereum via Eigenlayer, and integrating with Babylon for Bitcoin assets, they aim to build that solid foundation for their POS consensus.
Which, as we said, is crucial for a brand new chain.
Crucial, yes. That's how they frame it.
And the document also says validators can stake their own tokens, too. Not just the restaked ETH or BTC, like maybe a native G token or something.
Yes. According to the source, validators can stake certain permitted ERC20 tokens alongside the restaked assets. The total voting power a validator has in consensus is then calculated based on the combined value of all their staked assets, and this mix can be configured for each specific chain built with the SDK.
Interesting.
And they do note that the value derived from restaking that cross-chain value needs to be properly bridged over to the execution layer to be counted in that voting power calculation.
Right. Technical detail there. Okay, let's zoom out a bit to the overall architecture they laid out. The light paper says Gravity Chain is built on 2 main pillars: the Gravity SDK and Gravity Rigid.
Correct. The Gravity SDK is described as the modular open-source blockchain framework. It's presented as a refinement of Aptos, aiming to leverage its battle-tested parts, and that pipeline consensus we talked about.
Okay, that's the consensus there.
Right, and then Gravity Ruth is their execution layer. It's based on the rest Ethereum client, but specifically adapted to run in this pipelined way as something they call a Block Stream Reactor.
A Block Stream Reactor. Okay, and how do these 2 main parts, SDK and reth, actually talk to each other?
They communicate through a standardized interface. It's called the Gravity Consensus Engine Interface, or GCEI.
GCEI, got it.
And there's a pipeline controller that manages this interaction, so sort of adjusting things dynamically based on feedback it gets from both the consensus side, the SDK, and the execution side, reth. The fundamental design here is about decoupling block execution from block consensus.
Decoupling them.
Yeah, it makes the execution layer primarily just a consumer of blocks that the consensus layer has already put in order.
Okay, so let me see if I follow the flow described. Transactions come in maybe via RKC to Gravity Reth. They get passed to the SDK's mempool. They get bundled up. A validator proposes a block. Consensus agrees on the order of transactions in that block. And then that ordered block gets streamed back to Gravity Reth, the execution layer, to actually run the transactions.
That's the high-level flow they depict, yes. On the execution side, Grevm runs the transactions in parallel. The state commitment, like the state root, gets computed, but crucially, asynchronously. Consensus then just needs to agree on that state root before the final block and state data gets saved to storage.
Okay, let's dig into the Gravity SDK part a bit more. Why specifically base it on Aptos? What reasons do the sources give?
They list several motivations in the document. First, they view Aptos as, like we said, a cutting-edge POS chain with a strong PBFT consensus, noting that low latency from the 3-hop optimization.
Right, the order votes thing.
Exactly. They also really emphasize Aptos's proven performance. They cite its ability to handle something like 160,000 transactions per second with under 1 second finality on its own network as evidence that it's a solid foundation to build on.
So starting with something already known to be high performance makes sense.
Exactly. Plus, they mention its reliability in production, its fast innovation cycle, noting over 100 Aptos improvement proposals have been made, and frankly, the desire to not reinvent the wheel for complex parts like the mempool, state synchronization, block syncing, all that core stuff.
Right, leverage existing battle-tested code.
Precisely. Building on Aptos allows them, as they put it, a synergistic evolution. Gravity SDK can benefit from Aptos' ongoing improvements, and maybe Gravity SDK can contribute back by making the structure more modular and adding features like the restaking integration.
And that GCEI interface is the formal connection, the handshake, between the SDK and whatever execution layer is plugged in.
Correct. It's designed to be the standard communication bridge. It basically mandates that any execution layer wanting to work with the SDK must operate as a Block Stream Reactor.
Oh.
It needs to be able to continuously take in proposed blocks and calculate state commitments without blocking the consensus process. And importantly, it also needs mechanisms to handle transactions that might fail during execution.
Wait, handle transactions that might be unexecutable. Why would the execution layer even receive those in the first place? Shouldn't they be filtered earlier?
That's a consequence of the pipeline and asynchronous design, because execution of previous blocks might still be happening further down the pipeline asynchronously.
Right, it's decoupled.
Exactly. The mempool, when it's initially validating transactions, doesn't always have access to the absolute, very latest, fully committed world state in real time.
Okay.
So a transaction might look perfectly valid when it enters the mempool based on slightly older state, but by the time its block actually gets executed, the state is changed and it becomes invalid.
I see. So the GCEI and the Block Stream Reactor design need to gracefully handle that possibility, ensuring that failed transactions don't just grind the whole pipeline to a halt.
Exactly. Execution failures can't stop subsequent blocks from being proposed and ordered, otherwise the pipeline breaks.
Does the GCEI document define specific API calls for these interactions?
Yes. The source material does detail specific APIs for both sides. For the consensus layer, the SDK, and the execution layer. Examples include things like check the XN for the execution layer to do a sort of best effort validation for consensus.
Okay.
Submit edxn for consensus to send transactions to the execution layer's mempool, ordered block for execution to get the ordered blocks from consensus, update state commitment for execution to send back the results, the state root, and commit block hash for consensus to tell execution, okay, this block is final, persist everything.
Okay, clear roles and communication points defined there. Let's walk through that 5-stage SDK pipeline again, maybe with this GCEI connection clearer in mind. How do those stages really maximize resource use through interleaving?
Right. It's all about that overlap.
Okay, stage 1.
Transaction dissemination. Getting transactions spread efficiently between validators. This is decoupled from the main consensus ordering. They mention using ideas from protocols like Narwhal and Tusk to create certificates guaranteeing data availability, building on Aptos' quorum store component.
So making sure everyone has the transactions reliably. Stage 2.
Block metadata ordering. This is the core consensus step using Aptos BFT. It decides the final order of the block metadata and the transactions inside it. Once that order is agreed upon, this ordered block data is streamed via GCEI to the execution layer.
Got it. Stage 3.
Parallel transaction execution. Now we're in the execution layer, Gravity reth, using Grevm. The transactions from that ordered block are run concurrently here, using those simulation hints we talked about.
Stage 4.
State commitment. Calculating the resulting state changes, the new state root. This happens asynchronously from execution. The key point the source highlights is that this calculation does not block the next block from starting its own execution phase in the pipeline.
Crucial for keeping the pipeline moving. And stage 5.
State persistence. Finally, the committed state root and all the block data are written permanently to the storage layer, which they call the Gravity Store. This stage also signals back to the mempool to clear out the transactions that have now been fully processed and saved.
Okay, I think I've got it. Transaction availability confirmed, block order agreed, execute in parallel, calculate state changes kind of in the background, and then save to disk. That pipeline structure definitely seems geared towards maximizing throughput. Now, let's focus on Gravity reth. It's the execution layer. What were the key changes or optimizations they specifically had to make to a standard reth client to make it work within this very specific pipelined asynchronous setup? The docs must cover that.
They do. The source lists 4 really pivotal optimizations they had to implement. And these were necessary precisely because the SDK's pipeline model throws up unique challenges, like having to accept blocks that might contain invalid transactions, as we discussed, and that absolute requirement that execution results cannot delay the consensus process for later blocks.
Right. Okay, what's the first key ref optimization?
First is the Block Stream Reactor, BSR, concept itself. This is the core adaptation they made to Grevm, enabling it to continuously consume that stream of proposed blocks coming asynchronously from the SDK via the GCEI. It functions as a reactor pattern, and the source mentions it includes a dynamic feedback loop.
A feedback loop?
Yeah, using backpressure signals. If the execution layer starts falling behind consensus, it can signal back to slow down the rate of incoming blocks temporarily.
Wow, that's clever. Built-in flow control between the decoupled layers.
It's exactly. Smart design. Second key optimization. Decoupling state commitment from transaction execution. We've touched on this, but the source really emphasizes how crucial it is for enabling that asynchronous computation of state commitments. It lets execution of Block 101 start before Block 100's final state root is even calculated.
Okay.
And they explicitly mention having to change the very definition of block hash within their system.
Change the block hash definition? How so?
To remove the dependency on the state root being present in the block header at the exact moment the block's order is decided by consensus. This is a pretty fundamental architectural shift away from standard EVM block structures, done specifically to enable this decoupling.
Wow, okay, that is a fundamental change just to ensure that state root calculation doesn't become a pipeline bottleneck. What's the third optimization?
Third is optimization of the storage layer. This is about enhancing the storage engine underneath to be much more efficient at caching and saving the multi-version state values and commitments that this whole pipeline and parallel execution system needs. They mention using a multi-version storage engine and supporting fully asynchronous I/O operations.
Makes sense. The storage needs to keep up. And the fourth optimization for Grevm.
Parallel EVM execution, which basically loops back to integrating Grevm. They list this as the core optimization within their Gravity Rev layer, embedding that high-performance parallel engine to process transactions concurrently using the simulation hints and dependency graphs we discussed earlier.
Okay, so the BSR architecture, decoupling state commitment, even changing block hash, optimizing storage, and embedding Grevm for parallel execution. Got it. They also seem to dive a bit deeper into that asynchronous batched state commitment process. What's the specific bottleneck with state roots they're trying to fix there?
It's the inherently sequential nature of calculating a Merkle root, the Merkleization process.
Right, you need the leaves before the branches before the root.
Exactly. You typically have to compute the hashes of the subtrees before you can compute the final root hash. This can become a bottleneck, even with some existing parallelism techniques like the account-level parallelism reth already had.
So what are their specific innovations described in the paper to speed that part up?
They introduced two main things. First, asynchronous batched hash computation. Since the state commitment calculation is already decoupled and can be delayed, they can compute the state root updates in batches. Say, calculate one root covering the changes from the last 10 blocks, instead of doing it individually for every single block.
Ah, batching. That reduces overhead.
Right, reduces overhead and lets them more efficiently group together shared dirty nodes, parts of the state tree that changed, across multiple blocks. The second thing is full parallelization of the hash computation itself.
Going beyond just parallelizing by account.
Yes. They aim to parallelize the computation of the entire Merkle tree for all the modified nodes within a batch. They describe partitioning the dirty part of the tree into independent subtrees that can then be hashed concurrently by multiple threads or cores.
Okay, so batching helps smooth things out and reduce per block cost, while the full parallelization tackles the sheer computation needed for large state changes within a batch.
That seems to be the idea. And they mention one more related piece. An alternative fast state root calculation.
A different state root. Why?
This is needed for compatibility, specifically with Ethereum's block header structure and the block Galxe opcode in the EVM, which needs to access the state roots of the last 256 blocks.
Ah, okay.
Since their main fully verified state commitment might be delayed due to the asynchronous batching, they calculate a sort of temporary faster state root. The document says this is calculated simply as the hash of the block's change sets combined with the previous block's state root.
So it's like a placeholder state root, available immediately when the EVM needs it during execution without waiting for the real one from the async pipeline.
Precisely that. It ensures things like the block Galxe opcode, work correctly, and maintains EVM compatibility without breaking the asynchronous design of their main state commitment process.
Clever workaround. Okay, lastly, the Gravity Store. What's special about their storage layer, according to these sources?
It's described as a heavily fine-tuned, multi-version storage layer. It apparently builds on reth's existing storage foundation, which already does a good job of separating things like where the state commitments are stored versus the main state data itself.
Okay.
But for their specific Block Stream Reactor architecture, which needs to juggle state updates happening across different pipeline stages, potentially accessing different historical versions of the state simultaneously.
Right, because of the asynchronous nature.
Exactly. They utilize a highly efficient multi-version tree structure for the state data itself.
A multi-version tree, like storing multiple historical copies efficiently.
Kind of. The source explains that when state gets updated, the nodes that change are marked as dirty. The actual hash computation is deferred and batched against specific versions of the tree. This structure is apparently essential for supporting all the operations their pipeline needs, such as creating new versions of the state as new blocks get processed down the pipeline, querying state values from specific past versions, which might be needed for later pipeline stages, and also efficiently cleaning up or pruning old versions once they're definitely no longer needed by any active stage of the pipeline.
So it basically allows different parts of the pipeline, consensus, execution, state commitment, to effectively work on different snapshots or versions of the state without interfering with each other or blocking.
That's the core benefit described, yes.
It
enables that concurrency across the pipeline stages. They also briefly mentioned they're exploring developing their own custom storage engine called Gravity DB. Specifically optimized for blockchain workloads, supporting fully asynchronous I/O. They note the lead developer on it was also involved in creating a similar engine called Leadese previously.
Wow. Okay, this is really fascinating stuff. Getting down into the weeds of how they've engineered or plan to engineer this for serious performance, it's clear they've put a lot of thought into identifying and tackling potential bottlenecks at pretty much every layer described here.
The architectural choices seem very deliberate.
Okay, let's try and pull this together with a quick recap of the main ideas we've dug into from the Gravity Litepaper and docs. We started with that strong motivation, right? Driven by real-world application needs, like Galxe's volume, pushing them to an L1 design that absolutely prioritized low finality.
Yeah, that finality point was key.
Then we looked at the main building blocks. The Gravity SDK, adapted from Aptos for that pipelined BFT consensus, and Gravity reth, their specialized Block Stream Reactor execution layer built on reth.
The two core components.
We saw how parallel execution, powered by Grevm, and that whole 5-stage pipeline concept are just central to hitting those ambitious throughput goals. And these are supported by all those asynchronous processes we discussed, like decoupling the state commitment calculation and having that optimized multi-version storage layer.
Absolutely essential pieces for the performance claims.
And underpinning it all, we talked about the absolutely critical role of restaking, using things like Eigenlayer and Babylon to bootstrap security and gain economic trust by basically borrowing it from established networks like Ethereum and Bitcoin.
Right. And what really stands out looking at the details in these sources is how interconnected all these choices are. The decoupling via the GCEI, the asynchronous operations, the pipeline, the specific reth modifications, the multi-version storage. They all seem specifically designed to attack known choke points in more traditional blockchain designs.
It's like a targeted engineering effort to enable those headline performance numbers.
That's certainly the impression given by the technical descriptions.
So, okay, stepping back, what does all this technical detail mean for you, the listener? Well, getting a handle on the engine inside chains like Gravity, even just based on their planning documents, gives you a much clearer sense of what the future of Web3 applications could look like. It points towards a potential future where apps aren't constantly bumping up against speed limits or long confirmation waits, which could mean, much faster, much smoother, and just generally more capable user experiences in Web3 down the line.
And thinking about this deep dive into Gravity Chain's proposed architecture, it does spark a broader question, doesn't it? If we see more blockchain designs moving towards this kind of modularity, leveraging restaked security from big established networks, and really pushing the boundaries with parallel processing techniques like the ones described here, how might that fundamentally change things? Not just for the developers building the next generation of decentralized applications, but also for the everyday user. What does their actual experience look like when interacting with these potentially much faster, more efficient systems?
That's a really interesting thought to leave things on, a potential shift in what's possible, driven by these kinds of architectural innovations. The technical foundations we've discussed today certainly suggest the limitations we often associate with blockchains might look very different in the future. Great stuff. Thanks for joining us for this deep dive.